Traditional deep learning techniques are still far from how the biological brain works. However, they have been initially inspired by the brain's neural network. But moving forward, they are indeed evolving more and more as they become more sophisticated. And but there's still a lot of room for it. That's why, for example, neuromorphic computing space is exciting because it is one of the more closest way in which the brain processes information. And so today we're going to talk about some of these evolving neural networks. And then after that, we're going to dig deeper into how our brain at the biological level processes information such that it could potentially then inspire the future-looking technology within the space. Our current neural network, artificial neural networks, are more math-driven than biologically driven. And what we mean by that is that while their architecture and the way in which they process information was inspired by the brain and neurons, they were inspired more by very simplified version of how the brain processes information and how neurons work. And rightfully so, because initially when we started, there is just so much that goes into the brain that it becomes almost impossible to create artificial neural networks that work exactly like the brain, because a lot of times we don't even know exactly how the brain works. But for example, the rate-based activations is more likely to be embedded in the artificial neural networks and not the spike-driven, the way in which the brain works. Essentially also the static weights that we have in artificial neural networks are more embedded within them and not the dynamic synapses in which the brain works, and with the spike timing plasticity that we talked in last videos. And lastly, there are no brain waves or oscillations involved, the way in which also the neurons within the brain utilize and work, essentially. And when it comes to the biological way in which the neurons work. However, the newer, more nuanced and advanced artificial neural networks, such as the spiking neural networks that we talked about last time, are the ones that are gradually improving such that they could use the way in which the brain processes information. In this case, these spiking neural networks are artificial neural networks that use spikes, just like the brain, and these spiking neural networks use temporal coding, event-driven activities, and biological plausibility, as we talked last week. Platforms such as Nest or Brain2 or Loihi from Intel are helping to stimulate and run these artificial neural networks where neurons fire at discrete times based on the threshold input, as we talked last week. The networks encode information in spikes timing and spike rate, and also the training would be then harder because the gradients don't flow well through the spikes, but there's a lot of progress via surrogate gradients within these artificial neural networks. Moreover, the neuromorphic hardware are the ones that are also gradually evolving such that they are becoming more brain-like when it comes to them processing information and working as a whole. And these are the custom hardware built to mimic the brain's architecture and dynamics. For example, IBM's True North or Intel's Loihi, where they use spikes local plasticity rules and low power, just like the brain does. They often implement, for example, the learning, the plasticity learning that we talked about last time, as well as spike timing dependent plasticity, and also very energy efficient computation. These systems draw directly from neuroscience, especially when it comes to brain waves, fluctuating oscillation activities, sparsity, and distributed computation. There are also brain-inspired learning algorithms. So even if the artificial models, do not use spikes, there are some ideas from neuroscience that being brought over to this side of the tech, where, for example, attention mechanism like transformers have parallels with top-down modulations within the cortex. That's how the brain, for example, sometimes processes information. Predictive coding ideas are also starting to inspire the newer artificial architectures, as well as reinforcement learning, that in artificial intelligence it mirrors dopamine-based learning within the basal ganglia of the human brain, for example. And the idea is to go beyond just deep layers of these artificial neural networks and start build learning systems that resembles how the brain self-organizes. There's also something called the temporal dynamics and oscillations. And this is the least integrated aspects in the artificial intelligence today, but it is growing and it is improving, where neuroscience has shown that, for example, brainwaves, as in neural oscillations like theta, gamma, alpha, etc., play key roles in timing, coordinating, and attention, and as well as working memory within the human brain. And so these rhythms or oscillations synchronize neurons across different brain regions, allowing them to communicate with each other effectively despite the physical separation among the brain regions. And these are the phenomena and the way in which the brain of humans, for example, processes information that is giving inspiration to this future-looking artificial neural networks such as temporal dynamics and oscillations networks. There are some researchers that are growing in number who are working to build artificial systems that use oscillatory phases to prioritize, for example, or gate information. For example, theta gamma coupling as a mechanism for chunking or sequencing information when it comes to the information processing. Synchronizing models or subnetworks to enable flexible task switching, like the brain's dynamic routing of information, is also being researched. Moreover, encoding information not just in activations, but also in when activations occur, for example, in temporal contexts. However, while the current artificial neural networks don't yet model brainwaves frequencies like what happens in the brain, early research in phase-based computing, for example, and reservoir computing is testing how rhythm-based or oscillation-based processing might add temporal structure, context awareness, and adaptive control to artificial machine learning systems. And so for those professionals and researchers who are interested in learning more about how the brain works such that it would inspire the next generation of artificial neural networks, it's very important to understand more about the brain especially when it comes to its information processing. And so last week we talked a little bit about that. Today we're going to dig a little bit deeper into it. However, as always, I suggest that you learn more on your own because these are still very high level discussions that we bring up in this channel. And so it's important to understand that the brain is just not a passive decoder of information and of the sensory input that it receives, but it builds internal, dynamic, distributed patterns that looks at all the activities that it corresponds when it interacts with the world. For example, in a symbolic way, it creates these patterns or these images internally within itself, as opposed to going and decoding every single neuron firing one after the other, as we discussed last time. But in a relational and an emergent way is the way in which the brain looks at the world around it. And so the idea is that the brain becomes the map. It's a metaphorical way in which we talk about the brain's processing information capabilities that aligns with the work in predictive coding and active inferences, models that propose that the brain constantly creates internal predictions of the world and updates these internal images based upon sensory input that it received at any moment in time. In other words, spikes of the neurons are not messages with fixed meaning. These spikes do not come with, for example, tags that say, hey, this is a cat that you're looking at, or this is the color red that you're seeing. Their meaning is relational, context dependent, and they are built over time and layers of processing as we mature and grow older. Understanding these patterns is how we are increasingly improving. This is grounded in the idea of distributed representation and embodied cognition, where distributed representation means that no single neuron contains, for example, information about a cat that we are seeing. Instead, those experiences are encoded as patterns of activity across many neurons within the brain. In vision, for example, early studies showed that neurons in the visual cortex respond to edges, orientations, and or movements, but it's the population activity across many neurons within the brain that give rise to the perception of the whole object that we are seeing, for example. In primates, other parts of the cortex, for example, are involved in representing complex objects, including faces. And these neurons don't fire and say, oh, this is a face that you're looking at in general, but rather for a specific feature or a combination as such, it gives meaning to that pattern of neurons that are firing. And in system neuroscience, researchers are pushing the idea that the brain constructs meaning through dynamic patterns, not static codes, and it's not holding a stored or a blueprint of the world, but it's constantly reshaping these images of the world as it learns more and as it interacts more with the world. Early neuroscience borrowed the metaphor of communication systems. For example, they believe that spikes were messages. Neurons are senders and receivers. And this is called the neural coding metaphor. But more modern researchers they are arguing that this metaphor breaks down the biological brain, where a spike means different things depending on who it came from, when it arrived, and what the network state was at the time in which those neurons fired. A spike, for example, from one neuron could be part of many different meanings across different contexts. Therefore, the fixed meaning idea doesn't hold up in neuroscience anymore. Instead, spikes participate in dynamic population codes, not isolated signals. And for example, Brett has famously written that spikes are not messages, they are actions. And so neurons are participants in large neural networks of patterns. The idea that connects to, for example, population coding or neural dynamics, that where at any moment a neuron spike is just one part of a large pattern across thousands or millions of neurons within the brain. For example, in motor cortex, movement direction isn't represented by one single neuron, but by the vector sum of activity across a whole population of neurons. And this is called population vector coding, for example. In the hippocampus, place cells activating patterns that correspond to location in space, and no one spike represents that, for example, this is a cat, for example, but together the pattern of activity forms a spatial map of the environment within the brain. And in artificial neural networks, we also mimic this with distributed feature representation, where each unit contributes to a pattern that represents a complex input, not a literal label. And so meanings and thoughts within our brain arise not from individual neural spikes, but from the relationship among millions and millions of neurons and networks of neurons. And where cells tend to start firing together, they wire together, which we have heard also in the past. It's where the synaptic strength of a neuron grows from co-activity, not a symbolic communication. Also, temporal coding is the timing of the neural spikes that matter in relation to other neural spikes. And this is shown in, for example, in our way of smelling things, where the precise timing of input pattern is crucial of distinguishing odors when we smell something. Recurrent neural networks in the brain show that the context over time shapes the interpretation of that sensory input. The same input can mean different things depending on what came before or what else was co-activated. In perception also, this shows up as contextual modulation. For example, what we see depends on what is around it. A well-known example is the visual cortex, where neurons whose responses are influenced not just by what is in the receptive field, but by the surrounding activities that is happening at that time. Now, what about brainwaves frequencies in comparison to the neural spikes? While spikes in a neuron can carry potentially content, brain waves can potentially carry context. At least that's where we are researching and showing to some extent. So brainwaves frequency appear to not represent things in the way that the spikes of neurons are symbolically the systems do. Instead, they appear to act as organizer or modulators of neuronal activities. When it comes to timing windows of the spikes of the neurons, studies shows that, for example, gamma and theta brainwaves oscillation open windows of excitability during which the neural spikes are more likely to have an effect. For example, we call this communication through coherence, where neurons that are oscillating in brain waves in sync are more likely to influence one another. If two brain regions, for example, are oscillating together, let's say the same brainwaves frequency, they're essentially in the same listening or speaking rhythms, increasingly effective communication among those regions. And brainwaves in this example act like this encoding of the listening and speaking and communication among the regions, where it sets the timing for when spikes of neurons are more effective, giving meaning to when a spike occurs. In the hippocampus, for example, research shows that theta waves, which are lower brainwaves frequency, provide a framework, while gamma waves, which are much higher frequencies, ride on top of that framework. Each theta cycle contains several gamma cycles, and each gamma cycles encodes a different item in a sequence. This is the basis for example, some models of working memory, where brainwaves organize sequence of neural spikes, enabling the encoding of ordered memories, not just the firing events of these neurons. In alpha oscillations and sensory gating, alpha waves, which are around 8 to 12 hertz, especially in the visual and parietal cortex, for example, appear to suppress irrelevant information. When alpha is high, it is like a closed gate where it closes the input of information into the brain. Neurons are less than responsive to input from our sensory and from our environment. When alpha is low, on the other hand, the system appears to be more open to the external stimuli, let's say sensory information, and brain waves appear to modulate and control attention, which in turn shapes how the spikes in neurons are interpreted. Gamma waves frequency synchronization between different brain regions is also thought to help the brain to bind features into coherent perceptions. For example, how do we perceive a red ball, for example, instead of just something being red and something being a ball separately? Synchronized brainwaves frequencies, as in oscillation between different regions of the brain, may solve this binding problem by aligning their spike timing. Brainwaves align distributed neural activities, creating a unified experience out of disconnected feature, in this case, a red ball that is perceived as a ball that is red, not something separately. When it comes to predictive coding phenomena, in models of predictive coding, low frequency waves such as theta and alpha are thought to carry top-down prediction, and high frequency waves such as beta and gamma carry bottom-up sensory data. Therefore, when the brain is guessing what will happen next, as in predictive coding, it uses low frequency brain waves such as theta and alpha. When the sensory system corrects these guesses, it uses higher brainwaves frequencies such as beta and gamma, And this supports the idea that brainwaves shape perception by organizing the flow of information across in the brain and across different brain regions. In other words, brain waves, when we say that the brain doesn't encode a neural spike into meaning, but instead build patterns, brain waves are a huge part of how those patterns are organized in time. Brain waves don't contain the message, but they are like syntax or rhythm of a conversation. A neural spike that happens during one phase of a wave might have a big impact. The same spike during another phase might actually do nothing. So the brain waves act as a temporal scaffolding for perception, memory, attention, as well as decision making. The spike and wave interaction is extremely essential. Neither alone explains how their brain function. Therefore, anytime we talk about how the brain functions, how it information processes, how it communicates, we do need to have both the spikes of the neuron as well as the brain waves frequency of the neurons combined together. It's a marriage between the two. And this epiphany, this information is also extremely crucial when it comes to designing the future of artificial neural networks if you are in that business, because we do need to think about these coupling of spikes and waves together, because that coordination and information process happening in a such miraculous and beautiful way just because they are both coupled together. And there are some great literature that you can read or maybe look online if you're more interested. But for example, neurophysiological and computational principles of cortical rhythms in cognition comes to mind, or rhythm of the brain, and a mechanism for cognitive dynamics, neuronal communication through neural coherence also come to mind. These are some literature that you can read, and of course, there are plenty of other literature in the space as well. However, having said that, it's important to also remember that science is always ever evolving. Although we are moving extremely slow, we are making more and more progress as we move forward. And these type of scientific discoveries are and will be more and more important as to how we evolve also our artificial neural networks, such that we could design them to be much more efficient, exactly like our biological brain processes and handles information. Okay, I hope you guys find this topic useful, and thanks for watching. I'll see you guys next time. Bye.